Hello! In this video, we are going to prove the extreme value theorem, which says the following. Suppose f is a function from the closed interval a comma b to r, and f is continuous on a comma b. Then, f attains a maximum and minimum value on a comma b. In other words, we're trying to show that f has an output value that is greater than or equal to every other output value of f, and we want to show that f has an output value that is less than or equal to every other output value of f. Now, in proving this theorem, we are going to be using the fact that any continuous function on a comma b is also bounded on a comma b. So, start of the proof. Well, according to this result, we know that f is bounded on a comma b. And because f is bounded on a comma b, that means that the set of output values of f has an upper bound and a lower bound. By the completeness property of the real numbers, since the set of output values of f has an upper bound, that implies the set of output values of f has a least upper bound. We're going to let u be the least upper bound of the output values of f. Now, u is an upper bound of the output values of f, which means that u is greater than or equal to every output value of the function f. So if we can show that u is itself an output value of the function f, that implies that u is the greatest output value of the function f. Or in other words, that will tell us u is the maximum value of f. So that will tell us f has a maximum. So from here, we're going to show that u is an output value of the function f. And to show that, assume for a contradiction, we instead have u is not an output value of the function f. Well then, since u is greater than or equal to every output value of the function f, but not equal to any output value of the function f, well then u must be strictly greater than every output value of the function f. So then, the idea is, we consider the following function. We consider the function g from a comma b to r given by g of x equals 1 over u minus f of x. Now, it follows, since f is continuous on a comma b, we have that g is continuous on a comma b as well. The reason why just comes from properties of continuity. Since f is continuous on a comma b, and a constant function of u's is continuous on a comma b, well, the difference of those functions is also continuous on a comma b. But also, we know that a constant function of 1's is continuous on a comma b, so the ratio of these two functions will also be continuous on a comma b. So, g is continuous on a comma b. But remember, any continuous function on a comma b is also bounded on a comma b. So it follows that g is bounded on a comma b. Now we're trying to reach a contradiction, and the claim is we can show that g is not bounded on a comma b. And the way we're going to show that is by showing if we consider any positive real number m, we can always find an output value of the function g that is greater than m. So if we consider an arbitrary positive real number m, well then, since u is the least upper bound of f, well then anything smaller than u is not an upper bound of f. So in particular, u minus 1 over m is not an upper bound of f. Or in other words, u minus 1 over m is not greater than or equal to every output value of the function f. Instead, u minus 1 over m is strictly less than some output value of the function f, and we'll call that output value f of c. But remember, every output value of the function f is less than u. So in particular, f of c is less than u. But now we're going to modify this inequality so that the middle becomes 1 over u minus f of c. And to see how that happens, we'll notice, first, if we negate all three sides, that'll flip the signs of the inequalities. So we get this, but then if we add u to all three sides, we get this, but then if we take the reciprocal of these two guys, that'll flip the sign of this inequality. And we get this. But this is precisely g of c. If we send c into the function g, we get g of c is equal to 1 over u minus f of c. So this shows g of c is greater than m. What this shows here is, given any positive real number m, we can always find some output value of the function g that is greater than m. So g isn't bounded. But since from earlier we knew g is bounded on a, b, we've reached a contradiction. Our assumption that u is not any output value of the function f led us to a contradiction. So we must instead have that u is an output value of the function f. And because u is an output value of the function f, and u is greater than or equal to every output value of the function f, that's enough to say that u is the maximum value of f. So this shows that f has a maximum value. Now we want to show f has a minimum value. Now, we could do pretty much the same argument that we just did to show that f has a minimum value. But instead, we're going to do so by considering the following function. We consider the function h from a comma b to r given by h of x equals negative f of x. Now, since f is continuous on a comma b, well then its negative is also continuous on a comma b. So that's how we know h is continuous. And since h is continuous, well, we've just shown for any continuous function on a comma b, it must attain a maximum value. So we know that h attains a maximum value. And we're going to let v be the maximum value of h. Now, since v is the maximum value for h, we know that v is some output value of the function h. We can say v is equal to h of x1 for some element x1 in a comma b. And by definition of h, we know that h of x1 is equal to negative f of x1. And this tells us f of x1 is equal to the negative of v. So this tells us that negative v is an output value of the function f. But the claim is that negative v is the smallest output value of the function f. And to show that, all we got to do is show for every element x in the domain of f of x is greater than or equal to negative v. That will tell us negative v is the smallest output value of f. So, if we give ourselves an arbitrary element x in a comma b, well then, since v is the maximum value for h, well then v is greater than or equal to every output value of h. So in particular, v must be greater than or equal to h of x. But h of x by definition is negative f of x. But then negating both sides, that gives us negative v is less than or equal to f of x, or in other words, f of x is greater than or equal to negative v. So this shows, given any element x in a comma b, f of x is greater than or equal to negative v. So, since negative v is an output value of f, and negative v is less than or equal to every output value of f, that tells us negative v is the smallest output value of f. Or in other words, negative v is the minimum value for f. And so this completes the proof. And so yeah, that's pretty much it for this video.